Today, I would like to delve into mathematical function known as the gamma function. Interestingly, this function frequently emerges in IB questions without explicitly stating the name. My aim today is to provide a deeper understanding of the gamma function and explore its application, particularly in the context of IA writing. Without further ado, let's get started. In school, we come across three types of rays, alpha, beta, and gamma. Gamma rays have the highest penetration capability among them. Interestingly, in mathematics, we also have a function known as the gamma function, which much like its namesake, delves into into various fields within mathematics, just like the gamma function. Let's begin by defining this interesting function. The gamma function is defined through an improper integral and is represented by the capital letter gamma from the Greek alphabet. Its applications span across calculus, number theory, and probability, making it a versatile tool for various mathematical explorations. If this piques your interest, I encourage you to delve deeper, especially when considering potential topics for your IA or EE. Speaking of gamma, it's fascinating to note that in mathematics we encounter not just the uppercase gamma, defining the gamma function, but also the lowercase gamma, Euler's constant. Denoted by the lowercase gamma is particularly intriguing as it's tied to the harmonic series. This opens up another avenue for exploration, especially within the realm of the IA topics. The world of mathematics constantly unfolds with the layers of complexity and beauty. Embrace the possibilities and explore the connections. Who knows what insights and discoveries awaits in internal assessment journey. Today, let's examine a question from 2023 AAHM exam, specifically paper 3. I encourage you to pause and review this question. It delves into the realm of the gamma function, showcasing how it can be elegantly expressed as using factorials. But today, our objective is to derive the integral ourselves rather than being provided with the definition. This leads us to question, how does derivation reveal the factorial definition? What we want to do is to work with and play around with this gamma function to derive the n factorial instead of being given some clues. Beforehand, we were asked to do the improper integral and then try to find the pattern. But what if we didn't have it? And then what sort of techniques can give us the guidance to find this definition? To achieve this, we'll delve into a powerful method known as the differentiation under the integration sign, often referred to as a Feynman technique. This approach allows us to handle integrals that resist solution through elementary functions by determining their limits through improper integration. While I understand you may not have encountered this technique yet, for the purpose of our exploration into paper 3 and its learning phase, let's accept its validity and apply it to the forthcoming problems. I want you to pay particular attention to what I want you to be aware is that we are working on its differentiation on top of the integral, where we can actually take those derivatives inside the integral, but somehow it becomes a partial derivative. And if you ask me what the partial derivative is, we can talk about the discussion of the partial derivative compared to the implicit differentiation. So what is a partial derivative? Is it similar to the implicit differentiation? Is sort of a discussion we can have. Implicit differentiation is used to differentiate function where the dependent variables is not explicitly expressed in terms of the independent variable. In this method, differentiate both sides of the equation with respect to the independent variable, treating the dependent variables as an implicit function of an independent variable. So if you look at this circle equation, as you know, you will, even though the x and y are independent variable, y is described in terms of the x. Y squared is equal to 25 x squared, so they are pretty much the same thing. So the implicit differentiation is the method for the function that is not explicitly expressed by the independent variable. Here, y, even though y is a dependent variable, it is still described by the independent variable of the x. The partial derivative, on the other hand, is used for functions of multiple variables. It involves taking the derivative of a function with respect to one of the variables while considering the other variables as a constant. This is particularly useful when dealing with multivariable functions. So here's a quick example. For example, the x squared plus y squared equal to 25. You know the implicit differentiation would have been 2x plus 2y times dy over dx is equal to 0. That's the typical, the differentiation skills that we learn in IB curriculum. But partial derivative here, if you want to find, for example, only the rate of change of the x, you partial differentiate with respect to x, where you're going to get then only the 2x for your partial derivative. Whereas for the y squared, you would consider that as just constant compared to the independent variable of the x. Hence, it becomes 0 when you differentiate. So I want you to be aware of this new definition, which would have been presented in the beginning of the paper 3 question, because if it's unseen, it's likely either they give you for free, but give you some warm-up questions to learn the new technique. So now you have acquired these skills, for which now you can apply directly for the differentiation under integration sign. Okay, so now we're gonna delve into how to derive the factorial definition with the gamma function. But first, I want you to try with the following integral. So now let's have a look. Now this improper integral is trivial, as we can easily integrate exponential and evaluate the bound with the positive infinity as well as a 0. So the solution would have been given just integral of typical integral of the exponential function, which becomes negative e to the power of negative x. You just have to evaluate the limit. So as you know, it's exponential decay. So if you set it to infinity, it simply becomes a 0. Then voila, we have that value to be. So previously we had this improper integral being simply 1, and now what I want you to do, okay, as a paper 3 question, let's say the next section of the question asks you to do the integration by substitution. So if they have given you the substitution of x equal to tu, what we can do is perform the integration by substitution. As you know, I'm going to differentiate the substitution and then rearrange the dx in terms of du and try to express everything in terms of the substituted variable. And then integral now becomes of the following. The value remains the same. And here, what is a constant parameter that we can move around? As you have said before, yes, the constant value here is going to be in terms of t. The variable that I'm dealing with here is just in terms of u. That's my substitution. So now we have this cool result in terms of u. However, as we mentioned before, then t is now the constant parameter, whereas the u is the new variable, so we can rearrange the t to the other side. Now, therefore, the integral now becomes the following. Now I have this rational function, my friend. And please remember that the u is considered as dummy variable, right? It just doesn't matter which one we have to integrate by on the left and right. So it can be expressed in terms of u or other variable you like. But as you know, what we are typically using the integral is to describe everything in terms of x. So instead of working with the u, I like to actually change that in terms of x for the aesthetic purpose of this integral expression. So now we have this cool integral in terms of t and x, and then the value here becomes 1 over t. But I'm going to give you actually more challenging questions. So far, I have delved into this problem in the sentiment of paper 3 problem solving, where you are going to put under time pressure of 55 minutes of solving 2 problems. So sometimes you don't have to explain too much in details. Whereas, my friend, if you in the IA writing for the internal assessment, consistently reflecting on this question is crucial. So let's have a look at this. Why do we bother changing them from u to x? Having this value here, why is it necessary? Why under the time constraints, problem solving may allow for certain omissions. A research paper like the IA, however, which is granted a time frame exceeding 2 weeks, demands a higher level of academic rigor. This is particularly vital in justifying the inclusion of equations or the proof of theorems. It is important to bear in mind that a significant portion of the theorems you will present in your IA has already been established through the publication or proof. Therefore, your IA emphasize your personal reflections regarding these equations or proofs, demonstrating your understanding and insights into the mathematical concepts involved. For example, when we actually encountered this problem with the integration by substitution, we could have stuck with the in terms of u, but now we said, oh, I like to change it in terms of what is it? In terms of x for the aesthetic purpose. And that is correct, right? You could have continued with the in terms of u, no problem. However, because the theorem that we have learned, okay, because the theorem that we have learned was, what is it? It was in terms of the t and x. I like to use that theorem. Hence, instead of working with the u, I change it for the x. It's a convenience of the formula that we have learned. Because if this formula was, for example, if this theorem was described in terms of u and t, yes, you could have worked with the u and t. It's just aesthetic purpose. You cannot, from now on, just write it for as a granted for free. You have to justify why we changed it in your IA. Whereas for paper 3, you don't have to, because a lot of things can be omitted. Now, using this theorem we were given at first, supposedly from the learning phase of this differentiation under the integration sign, what I want you to do is to try to differentiate both sides with respect to what? What differentiation would you like to do? Very good. According to the theorem, I like to differentiate back to t. So let's try to do that. So if I try to differentiate this with respect to t, the right-hand side will be just typical derivative. It will become just negative 1 over t squared. And then for the left-hand side, where you can use the notation under the integration sign, what you can do is to take the derivative inside of the integral, becoming the partial derivative. And now, what I like to do is to differentiate that e to the power of negative tx with time t, and where then it becomes just chain rule. So we have that. So please notice we are able to use the differentiation under the integration sign, and inside the integral we perform the partial derivative of the exponential function, for which we simply use the chain rule with respect to time t. Therefore, the derivative of inside the function comes out as simply negative x when we multiply, and then we're going to compare these two. So therefore, we have the left hand side and the right hand side being equal by using the differentiation under the integration sign. And then, what we can do, my friend, is just fancy differentiating with respect to time t, and then let's try to do so. On the right hand side, we see repeated pattern of just differentiating with respect to t. We can use the power rule, no problem. On the left hand side, yes, you can use the differentiation under the integration sign again. That we will simply have the following. It is just a quick derivative of the exponential and the partial derivative within the integral. So you can check yourself very quickly. So far we have, the first derivative was given as such, for the second derivative was given as such. So continuing this process, we can have this pattern here, that pattern, and that pattern. So if you actually pay closer attention to the numerator, my friend, we had a 1, 2, 6, 24, 120. And if you actually continue to look at this pattern, you realize the 6 is simply the 3 times 2 times 1, so hence the 3 factorial, 24 is a 4 factorial, 120 is 5 factorial. So now, what we like to do is to see the generalization. If you continue to differentiate this further, what you see here is that you're going to have some n factorial in the numerator over the t to the power n minus 1, whereas left-hand side, we're going to continue to multiply the x because of the chain rule done by the differentiation under the integration sign. And here, to derive the pattern, that to see the gamma function that we saw from the beginning, what value of t would you like to use to make it neater? Very good. If you put just t equal to 1, then voila, we do have this gamma function that we wanted to describe. So that's the generalization. All right. So this approach that we just took will be the approach discussed typically for paper 3. Okay, we managed to use the technique given from the learning phase to derive something classic as the gamma function. We call it as a proving phase. But I want you to realize it has completely different sentiment when it comes down to writing an IA about the function. So far, we just solved the problem, or rather being able to apply the technique to locate the right piece of puzzle in the board. When it comes down to the writing of paper, you should always question yourself why in your sentence. This theorem has already been proven by someone else hundreds of years ago, centuries ago. Why should you write it, and why is it containing any personal reflection is the fundamental question. For mathematical question, why in this problem, when we were using this differentiation under the integration sign, why did we want to express things in terms of x and t, and how differentiating with respect to t gave me a rational function, and how finding higher order of the derivative actually derived the factorial. Those type of discussions should be the primary focus of your IA. Remember, most of the results, including this question, has been shown pretty much everywhere in the calculus textbook. Why should your paper be fresh from them is the main focus of your writing. Okay? Moving on to our next example, this one really highlights how we emphasize showcasing personal insights and reflection in our computation. So let's dive in and take a closer look at this beautiful Dirichlet integral of the following function. You might have seen quite often actually. So I like to talk about how this integral can be improper integral can be evaluated by the by differentiation on the integration sign. All right, let's have a look at this nice function for finding using the differentiation under integration sign. So let's have a look. So what I like to show you is the behavior of the sine x over x on the xy plane, and as you can see, it's just simply the even function. And then using the symmetry, later on, what I like to use is defining the area. Well, I get it. So it's not really finding the area, because what we want to do is to look at the behavior of the integral from negative infinity to positive infinity. As you can see, certainly deals with something with the positive region as well as the negative region. So we're not going to be actually call it as a finding the area, but finding the integral. So as you can see, from negative infinity to positive infinity, we would like to see the behavior of this function. So that's why we call it that the negative infinite to positive infinite for the integral is the improper integral that we want to find it. And what we want to show is that it actually ends up being pi using the differentiation under integration sign. And we like to use y. So Dirichlet's integral holds paramount significance for a multitude of reasons. It frequently emerges in pivotal mathematical domains such as Fourier transformation and number theory. Often categorized as a special function, it possesses a unique characteristic. Its indefinite integral eludes a simple elementary function, unlike familiar functions like trigonometric, exponential, or hyperbolic functions. There's no straightforward classic functions that can encapsulate and define this integral. So we often just call it as a sine function. Okay. So we'll try to apply the differentiation under integration technique to solve the following integral. So commonly, so then I like to tell you something. I like to tell you in this integral. So commonly, all right, all the textbook, which has the purpose of teaching you how to apply the technique efficiently, we'll start with this integral by multiplying, my friend, of e to the power of negative tx, and then perform the differentiation under the integration sign. And yes, this is going to get you the answer. Of course, every textbook has all the answers and the solutions. However, this is not how you should start with your IA. Okay, you must give your reflection in the questions. And what is so here, who is the unexpected guest? Somehow, when I was trying to evaluate the improper integral from 0 to infinity of a sine x of x, I started with this exponential decay function. But really question yourself is, how on earth can we come up with the fact that we have to multiply this exponential decay function to make the differentiation of integration sign simple? Okay, so that is the key. We know there's no elementary solution for this function, but we must evaluate this improper integral becoming the pi over 2. Okay, and then we said that yes, you can try yourself, but doing the integration by substitution or integration by parts does not give you anywhere. Although you can actually use the integration by parts to prove for the convergence, I believe. You can use the integral comparison test and integral test to prove the convergence, but finding the actual limit actually involves much more advanced technique. And here, if you actually consider for the integral, what is the unknowing term to work with? Those are the questions you need to write about. You need to talk about your personal exploration of a topic. If I have a sine x over x and I wanted to integrate that, the unknowing part here, my friend, is actually who? Very good. 1 over x is very annoying. Okay, so we have established that for the evaluation of integral, we want to get rid of the 1 over x. If you can get rid of it, that would be lovely, right? And we want to use the technique of differentiation of the under the integration sign. Okay, so I need to think about a function that I could possibly get some help when I do partial derivative with respect to time t to get rid of the 1 over x. There are many options to consider. For example, another sine function sine tx will yield the partial derivative of x times cosine tx, where it will get rid of 1 over x when it's multiplying with the original function. However, if you actually think about the integral afterwards, it will get very nasty. Okay, let's have a look at the following differentiation under the integration sign by using this extra term such as a sine tx and then use the partial derivative to break it down into the function as the product of the cosine and sine. And for this one, sure, I'm certain you can continue the process with more techniques from trigonometry, such as a product to sum formula, like the factor formula that we typically learn from the trigonometry. And then this technique is often used for actually finding the crucial terms in the Fourier series. However, we should always pursue simpler technique when it's available. Can you consider a function that will get rid of the 1 over x and still gives us a nice improper integral to work with? Because if you look at this, sure, even though you should be able to use the product to sum formula, I'm sure the integration would be quite nasty. We often don't like the product of a sine and cosine, especially when they have a different period. Okay. We actually saw the function many times on our IB exam, and I'm telling you, whole point of encountering a challenging problem in the IB exam is for the examiners to promote the interest within you with this historically important or beautiful mathematical foundings. So let's have a look at the next function, and then I really hope that you actually see this partial integral of the product of exponential and sine. Okay, and we see this integral very often in paper 1 and 2. A recent exam paper have 1 or 2 questions already with this function, and I want you to realize why this function is popular is that it's actually very crucial in physics, as it deals with something called a damping oscillation. But for this one, you don't have to know the practical application of the function at the moment. What I want you to stick with is actually to work with the techniques of the integral. Anyways, on our focus here is to work with the technique of integral, for which we're going to do the integration by parts. And as you know, for the product of the exponential and sine, yes, you're going to actually do the integrate by parts twice. So then if you actually do that and do the rearrangement with the like term, I hope you will be able to see this following integral, and I'll leave it as an exercise to you. It's actually very standard integral, and this will certainly help with the differentiation under the integration sign. So here is the thing: if I had that sign x over x, and my job was to get rid of the 1 over x, right? We had to get rid of the 1 over x, and the first function that we come up with is, okay, what about the similar function such as a sine tx, and then do the partial derivative of t, and it's gonna take out the x in the front, so it's gonna cancel out with the 1 over x. However, sure, I want it to be easier integral after the partial derivative, and for this one we already have this function in our hand. This exponential, the product of the exponential and sine is a typical example with the integration by parts, and I'm sure you can use it. Okay, so instead of multiplying by the sine tx, I like to multiply with the exponential e to the power of tx. I'm sure you have seen some questions related with the infinite geometric series for the evaluation of improper integral as well. Okay, so what I want you to try is the following. That is why multiplying the exponential really helps the differentiation under the integration sign works. It deletes the variable x, hence now it's a workable integral. And then the fact that it's exponential decay makes the value converging to 0 rather quickly. Therefore, what we want to do is to call the integral of the capital letter ft as the following: the improper integral from 0 to infinity of the product of the exponential decay e to the power negative tx sine x over x. And I really want you to realize, why have I chosen that function? We could have chosen the other functions such as the sine, log, whatever, to bring out the partial derivative as so that it's going to come out with the x in the front using the chain rule. Hence, it's going to cancel out the 1 over x, because the initial integral that we wanted to work with, of the sine x over x, has been rather difficult because it didn't give us any elementary function to describe. However, among many options, the reason we chose of the exponential decay helps us to integrate really quickly for the evaluation. So for the integrand here is with the product of the exponential and the sine x over x, where the partial derivative with respect to time t will just become like the product of a sine and exponential by getting rid of the, and now I only have to deal with this, right? This is a lot more beautiful, because we can use the result from the previous section where we introduced the integration by parts solution with these function. You can use it for the general purpose. So if I did, by letting the a to be t, and then we can evaluate rather quickly as the following, right? So all you gotta do is to consider what's gonna be the limit like when you send the x to the infinity. So think about it. If you send x to the infinity, the sine and cosine will be oscillating. There's no doubt about that. But because the exponential decay is so powerful, it converges to 0 very quickly, the entire thing will become actually 0. And if you put x equal to 0, sine sine is going to be 0, so you don't have to worry about the t, and the cosine is equal to 1, and exponential function with the x equal to 0 would become simply just 1 with the exponent of 1. Hence, it becomes just 1 over 1 plus t squared. Hence, our differentiation under the integration sign will result in the following, right? That integral would become so negative 1 over 1 plus t squared after evaluating for the infinite and 0. Now we have successfully managed to get the improper integral, for which we know it is after differentiating with respect to time t, both sides, and then right hand side becomes some function's derivative. You want to find out what the initial function before the differentiation. What do? We need to use the anti-differentiation, which is called integration. So using the fundamental theorem of calculus, the right hand side would appear to be something more familiar, right? What we want to do is we have this result, and to bring it back with the f, right, we can use the fundamental theorem of calculus. So we are going to integrate both sides with respect to time t. And I want you to remember, sure, the right hand side looks very familiar, isn't it? Okay, and yes, in fact, that is the inside. That would be the arctangent, right? The integral will come out to be the integral. So we want to find something definite, right? So it's probably better off using some initial condition, and using what you want to do is to use your best bet, because you want to find the constant c, right? And now we are dealing with the arctangent, and we need to play around with the parameter t, right? And then the t will also affect on the left hand side, right? And can you think of outside the box, special angle to associate with the arctangent, right? So t, if t is 1, the arctangent will come out as just pi over 4. T being root 3 will come out as a pi over 3, things like that. You have to consider what values you want to do. But the fact that it not only does it involve the arctangent, but also the exponential or decaying function, if you send to t to infinity, things can be more interesting both sides, right? Because if you send t to infinity, the arctangent will actually turn out to be pi over 2, right, for its horizontal asymptote, as well as the left hand side will simply become 0 because of the exponential decaying property. It is converging to 0. So in fact, the left hand side, I don't have to evaluate the integral. It will be simply just becoming 0, and hence you can find that constant c from the indefinite integral, which becomes a pi over 2. So my particular integral that we are doing will be involving the pi over 2 minus arctangent t right hand side. So now we play around with the t being infinity. How about we take the t to 0? What if I take the limit t to 0? Then why have I done that? Because, well, arctangent 0 is simply 0, so it's gonna be pi over 2 on the right hand side. On the left hand side, my friend, so if we actually send t to 0, exponential term simply becomes a 1, hence making the left hand side as the integral that we wanted to get. Okay, so this is correct. So the whole point of the sentiment, the way I write of introducing this solution was somewhat different from the gamma function. I hope you see the subtle difference. For the gamma function, we were like bulldozer. We were given the clue, we were given the technique, we just use it text. And that's the whole purpose of the textbook, college textbook, because they want to efficiently teach you the text so that you can pick it up and use it. But for the writing perspective, you got to be careful. You got to be careful how we can use this differentiation under the integration sign, pretending that we didn't have many clues, that we didn't get that we had to multiply this exponential function. What you had to do instead was, okay, I can't do the integral of a sine x of x alone because it doesn't have any elementary solution for the indefinite integral. So I would like to get some help by multiplying a function so that the integration becomes much easier. I could have come up with the sine sine tx, where then it would have got rid of the difficult terms such as 1 over x using the partial derivative / chain rule. However, and the integral following up with that was actually quite demanding, and I like to consider the different function such as exponential, because the product of exponential and sine has been a quite popular trend of the typical example in the integration by parts. So as you can see, you really have to ask why we put these terms and why we are using the technique. That is the sentiment of the writing an IA. You really have to justify, but that justification shouldn't come mostly from the textbook, but from your own personal reflection, from your own intuition. The way you write that is really truly make the paper more authentic. So that's very, very important. And yeah, in fact, you can elaborate two seemingly unconnected functions such as a Dirichlet integral and gamma function together. Here's actually a nice expression of a more general Dirichlet integral in terms of a gamma function, right? And where that was the gamma function. I believe it is certainly a great example to write on the extended essay. And then, do you want to see something more fascinating? On many textbook, a lot of textbook uses the sign x over x actually to derive something called a Baza problem, where it was a sum of the sum of the it's a zeta function. So sum of the rational function is the following, converging to with the limit involving the irrational number of the pi, in fact square. Okay, you can actually, in fact, you can associate gamma function to prove for the proof of the Baza problem, and extend furthermore with a zeta function with the even numbers, such as the 1 over integer to the power 4 can be also derived using the gamma function and using this something similar to the Dirichlet integral. So if you're interested, of course you can delve into more. Right, it's a very exciting functions, and that's why we have many questions like that in the exam. Right, and it is no joke. You have seen something like this on exam questions. Examiners are trying to present you enticing ideas from the history of mathematics to enhance your understanding as well as elaborate the topics you have covered with syllabus with elegant solutions. In 2023 May, we saw gamma function, and also I would like to point out that we have seen from 2021 May exam that is not exactly the same, but very similar. It actually reveals we were on the pathway to find the gamma function up until the 2023. What you see on the right hand side actually has some similar name to the gamma function. It's actually called the beta function. So that function itself is not beta function exactly, but integrating the function actually associate with the beta function. All right, it is called the beta function when you start using the improper integral. And surprisingly, yes, you can connect with the gamma function as the name. So that's the beta function here, and then you can also connect them with the gamma function. Now, of course, as you can smell, this is a very elaborate example that you can associate for the extended essay. So to summarize what we have achieved, we briefly talked about the capital G, capital gamma function, right? That is a beautiful. And then lowercase gamma, although we didn't discuss it much in detail, it is certainly a great topic for the internal assessment. And then we extensively discussed about the differentiation under the integration sign. We showed an interesting example with the actual deriving method of the gamma function as well as the Dirichlet integral. Right, so those are that has been a good example to play around, right? The differentiation under the integration sign for this, and this is all the constant, or typically known as the lowercase gamma. And also we briefly mentioned about the beta function. Not only should you be able to use this method, but also contemplate, my friend, right? Contemplate why those techniques, certain functions prefer to be used when we differentiate under the integration sign, right? Please remember what we need. We always want the efficiency as well as the precision. Understanding why we chose exponential decay function for the Dirichlet integral would really put you in a different level of understanding to write a great IA for your future. That's the beta function. Right, so that is pretty much it for me today. I hope you enjoyed the video, right? I really want you to know the big difference between the sentiment you'd have to take for the paper 3 and internal assessment by taking a look at this very nice example proposed by the IB, right? For paper 3, it's time pressured, so you don't have to write too much of a detailed proof. However, for the internal assessment, you are given this time frame of weeks or more, so you are expected to write much more in rigor for your mathematical equations and solutions. Okay, so I hope to follow a bit more interesting video for you next time, but that is pretty much it for me today. In case I don't see you, good afternoon, good evening, and good night.